All right, we're about to pull back the curtain on one of the most common, yet kind of mysterious things in medicine, the good old blood test. So, let's dive right in.
You know the drill, right? You give a little vial of blood, it gets whisked away behind a lab door, and then a report just kind of appears. But what actually goes on inside that black box? How on earth does a machine make sense of the millions of cells that are just swimming around in a single drop of your blood?
Well, today, we're going to take that tour. We're going to follow your sample, step by step, and really unpack the incredible tech that turns your blood into that critical health data.
Okay, so the very first challenge is just a numbers game. But we're talking about a massive scale. A tiny drop of your blood has millions of red cells, thousands of white cells, and hundreds of thousands of platelets. How do you even begin to count all of that accurately?
The answer isn't some crazy, complex magic. It's electricity. The main way these machines count cells is based on a principle that is just beautiful in its simplicity. It's all about creating tiny, measurable interruptions in an electrical circuit. So here's how it works. First, your blood gets diluted in a fluid that conducts electricity. This basically just spaces all the cells out. Then, that stream of cells is forced through a microscopic hole. It's so narrow, only one single cell can pass through at a time. And as each cell squeezes through, it briefly breaks an electrical current, which creates a little pulse. So what's the machine's job? Just count the pulses. 1 plus equals 1 cell. That's it!
That little electrical blockage has a scientific name: impedance. See, blood cells are pretty bad at conducting electricity compared to the fluid they're in. So when a cell gets in the way of the current, the resistance shoots up for just a split second. And that's the exact signal the machine is listening for.
But here's where it gets really clever. This method does more than just count. It measures, too. A big old red blood cell is going to create a much bigger electrical pulse than a tiny little platelet. The size of that pulse is directly linked to the size of the cell. So from the very beginning, the machine isn't just counting, it's already sorting by size. But, counting and sizing, that's not enough, especially when you're talking about your super complex immune system. To really figure out what's going on, we need to be able to classify all the different kinds of white blood cells. And for that, we need a whole new tool. We need light. So how does light help? Well, after the cells have been counted, they get lined up single file all over again. But this time, they're shot through a laser beam. This technique is called flow cytometry, and it gives us a much more detailed picture of every single cell. As the laser hits each cell, sensors are measuring how that light scatters. The light that basically keeps going forward tells us the cell's size. But the light that bounces off to the side, that reveals what's inside the cell, its internal complexity. Is it smooth? Is it grainy? That side scatter gives us a peek at the cell's internal guts.
And this combination of data, the size and the internal complexity, is what lets the machine create that detailed 5-part differential you see on a report. It can tell the difference between a big complex neutrophil and a small simple lymphocyte. It gives doctors a really clear snapshot of your immune system.
All right, so we've counted the cells, we've sorted them, but what about one of the most important things in your blood? Hemoglobin. That's the protein that carries all the oxygen around. To measure that, we have to switch gears entirely, from physics to chemistry. Yeah, this process is completely different. First, a chemical reagent is added that literally bursts open all the red blood cells, which lets all the hemoglobin out. Then, that hemoglobin gets converted into a stable compound that has a specific color. And finally, a beam of light is passed through the whole solution to measure how much of it gets absorbed. That first step, the bursting open part, has a name. It's called lysis. It's a really fundamental technique in any lab. It's just the controlled destruction of a cell so you can get to whatever's inside. Without lysis, the hemoglobin would just stay trapped and we'd never be able to measure it.
And this whole process is incredibly precise. The machine doesn't just use any old light, it uses a beam with a very specific wavelength of 540 nanometers. Why? Because that is the exact wavelength that this colored hemoglobin compound absorbs the best.
The relationship here is actually pretty direct and beautiful. The darker the solution gets, the more light it has absorbed, which means there's more hemoglobin in there. It's a really simple but super effective way to measure the concentration. So, we have these 3 amazing, totally separate technologies all running at the same time: electrical pulses, laser light scattering, and chemical color analysis. So how does all of this get put together into that final report your doctor sees?
Well, to bring it all home, the machine has gathered millions of data points using these three core methods. You've got the electrical impedance to count and size the cells, you have the light scatter to classify them, and you have light absorption to measure the hemoglobin. Each method gives us a different piece of the puzzle.
And the analyzer's computer, well, it's the final translator. It takes all of this raw data, the pulses, the scatter plots, the absorption levels, and it crunches it all into that clean, organized, complete blood count report, even flagging any numbers that fall outside the normal range.
And that really brings our tour to a close. This incredible technology, which honestly used to take up an entire room, now fits on a countertop and is a cornerstone of modern medicine. And it really makes you wonder, what's next? What happens when this power of analysis gets so small, so cheap, that you could monitor your own blood counts every single day, right from your own home? The implications are just fascinating to think about.